Good afternoon, all. This is a video on advection and instability. And let's go into the forecasting program so we can see or remind ourselves how the program scores both instability and advection. And then, of course, we'll define each. So I'm going into 00 forecast, click on complete. And so questions number 5 and number 9 deal with advection. And recall that we defined advection as the horizontal transport of some property, in this particular case, temperature. We can also move moisture from the Gulf of Mexico horizontally from the south up to Iowa, but we are only forecasting for temperature advection and not moisture advection. So let's see how the program grades for temperature advection. I've already talked about this in a previous video, but it's always good to go over it again. So again, here's the definition of what advection is. It's just a horizontal transport, the horizontal movement of temperature by the wind. And you know this intuitively, especially when you get strong southerly winds during the summer or even during the winter. There are times we can get some strong southerly winds that are bringing up warmer temperatures from the Mid-South region of the U.S. So the program actually looks for significant advection if you have at least a 1 degree change in temperature due to advection. Now recall, you can have a change in temperature due to incoming solar radiation from the sun, which is shortwave radiation, and also longwave radiation from objects such as buildings. Clouds themselves emit radiation. We're learning that currently in Chapter 2. So we're not talking about an increase in temperature due to radiative processes. We're talking about in terms of significant advection. So the program looks for at least a 1 degree temperature change due to advection that occurs in the 2-hour period preceding 18Z. In other words, we're looking to see if the change in temperature brought on by advection occurs from 16 to 17Z and 17 to 18Z. Now, basically, a good shorthand notation for this of identifying advection is looking at wind speeds of at least 10 miles per hour blowing across isotherms. Recall earlier we talked about isotherms being lines of constant temperature. And these isotherms have about a spacing of 10 degrees Fahrenheit over about a 200-mile horizontal distance. Here's an example of advection. And you see here the state of Iowa. And you see the isotherm I'm outlining here, 10 degrees Fahrenheit over northern Iowa and 20 degrees Fahrenheit over southern Iowa. You see there's a 10-degree temperature change, and the station models indicate 10-knot winds. So that right there tells you that you would have at least significant advection. And in this case, since the winds are northerly and the temperature is decreasing as we get to the north, we're bringing in cold air advection. So that is an example. Now, if these wind speeds were less than 10 knots, let's just say there were 5 knots, then yes, it would be advecting cooler air, but not significant cold air advection as what is defined by the computer program for those 2 particular questions on the forecasting exercise. We've got this particular link here helps you with some PowerPoint slides, and I would encourage you to visit those and look at those and let me know if you have any questions. And here is another example of cold air advection, one that I put up several years ago, back in 1997. I guess that's 15 years ago now. Notice I have a minus 15 degree isotherm over northern Iowa, a negative 5 isotherm over southern Iowa, and wind speeds 20 knots. So we are bringing in significant cold air change because of the strong winds and the colder temperatures. Now keep in mind, you don't have to have your isotherms oriented north to south. You can have isotherms oriented west to east. if I could draw on here, you could have a -5 isotherm here, a -15 isotherm here, and if you have a westerly wind, then you're bringing in warmer air. So this is just one of many examples that could occur. Here's an example of warm air advection. Notice here, I have a -5 degree isotherm and a -10 degrees Celsius isotherm. So now there's only a 5-degree difference, but notice the winds are 20 knots. So if you were to use this formula down here, temperature advection is the wind speed, in this particular case, 20 knots, times the change in temperature across about 200-mile distance. If you look at this, the change in temperature is 5 degrees Celsius. You multiply the change in temperature, 5, times the wind speed, which would be 20. That would give you 200 over 200, the distance, which would give you a change of 1 degree Celsius over that particular area. So really the easiest way to do this is let me just give you an example. Let's take a look at a real-life example. And if I go back here, and we're going to go back here to our Scholar site, and specifically to the maps to use for forecasting. Notice I've got a link here, a surface map for temperature advection. Let's click on that. Now, what we're seeing is a very interesting pattern here across Iowa. Notice that temperatures along the northern border of Iowa, 65, and then it goes 70, 75, 80, 85. We currently have a 20-degree difference in temperature across the state of Iowa. 20 degrees, and notice the winds are 10 to 15 knots. So what type of advection is this? Well, I see a southeast wind here, a southeast wind here. So winds are coming from the southeast into Iowa, and it's bringing in warmer air. So that must mean we have warm advection, because we'll be bringing in warmer temperatures as we go through time. Now let's just calculate advection here just for a moment. And the number that we're looking for is 100. And I'll show you what I mean. So recall that we had temperature advection is equal to the wind speed times the change in temperature divided by a distance. The wind speed that we saw from this particular map, we're seeing 10 to 15 miles per hour, 10 here, 15 here, so let's take the average of that. So that would be 12 and a half. I'm going to round it to make it a little bit easier. So the wind speed is 13 miles per hour times the change in temperature. We saw that there's a 20-degree change in temperature. And north to south across Iowa is roughly about 300 miles. But I'm going to leave off the distance for this example. And so if you take 13 times 20, that is equal to 360. Now let's not worry about the units at this point. So actually, if we do use the units, we've got 360 miles, degrees per hour. But the number that we're looking at here is 360. If you take your wind speed times the change in temperature, and that number is greater than, is at least equal to, or greater than 100, then you have significant advection. Now this isn't calculating out the entire equation of advection. I'm just giving you a quick kind of rule of thumb that you can use. Take the wind speed times change in temperature, and if that's greater than 100, then you have significant advection. If it's not, then you do not. So just by looking at this one map here, which we got from this Maps to Use for Forecasting, specifically Surface Map for Advection, and we see that the isotherms, in other words, temperatures changing rapidly across Iowa, and you have at least 10 knot winds that are bringing in the warmer air. And we did the part of the calculation. We took the wind speed times the change in temperature, and that was 360. Then we have significant advection. So that gives you an idea. So this is part one of the video on advection and instability. I'll follow up here in a few minutes with the instability video. Let me know if you have any questions.